Welcome everyone to today's webinar. It's my great pleasure to introduce the first speaker. So we have now today two speakers. The first speaker will be Mehran Poursoltani. Mehran is a postdoc at McGill University, and he was a PhD student at HSC Montreal, supervised by Eric Delage and Angelos Giorgio, and he's doing research on robust optimization, regret minimization, risk management, and this area. And today he's going to talk about robust data-driven prescriptiveness optimization. So without further ado, Mehran, the mic and the screen is yours.
Thank you so much, Professor Ahmed Reza and Yanis, for the invitation and the opportunity. Today I would like to talk about the robust data-driven prescriptiveness optimization. This is a joint work with Professor Eric Delage and Professor Angelos Giorgio, my PhD supervisors, and I have feel so honored to do my PhD under their supervision. And this is the third chapter of my thesis. Let me dive into the outline of my talk. First, I will start with some introduction about the basic concepts and the research question. Then I will introduce the new model that we are proposing in this work. Then I'll share some results about the numerical experiments that we had, and finally, I will conclude my talk. Let's start from the traditional definition that we have for the stochastic programming. We know that in the stochastic programming, we would like to, for example, minimize an expected value of a cost function. Here at the top, we have a problem that we are minimizing the expected value of h. H is a function of x and psi. X is the decision variable vector that we have, and psi is the random variable that we have in the problem. Just as an example, I have a shortest path problem here. We have an origin and a destination. We would like to find the shortest route between these two nodes. We can think of different routes that we can take. And we can think of it as a network that we have different arcs and nodes on that. And historically, in the stochastic programming, we have some historical information about the travel times over these edges or arcs that we have. On the right-hand side, you see that, for example, we can have some histograms and frequency diagrams for these travel times over the edges. Psi, as I said, is representing the traffic demand with distribution F, and X is the shortest path route, actually, that we want to take. And we can take the stochastic programming paradigm to solve this problem. But the thing is that these days we have access to plenty of data, okay? Like site information, more than what we already knew about the historical demand travel time over these arcs. As a result, people started to work to concentrate on actually a new paradigm called conditional stochastic optimization, or CSO. In this problem, in this type of problem, we are actually trying to consider the site information that we have in hand. We would like to again minimize the expected value of a h function, but it is conditional on zeta. Zeta is here is representing or denoting the site information that we have. For example, let's say that we have in the data in the data set that we have some records for some work days or holidays that we have. In the traditional stochastic programming paradigm, we are normally looking in the histogram of the blue that you see on the right, and we are actually looking into the aggregate histogram that we can get from this data set. But when we are trying to focus also on the site information, somehow we can distinguish between the two different parts of the data set, conditional on the workday or conditional on the holiday. As a result, in this paradigm, we have psi, which is the traffic demand. Zeta is denoting the workday or holiday as site information. F here, the distribution that we have is the joint distribution of zeta and psi, and we need the conditional distribution to be able to solve this problem. In normal practice, we don't have normally access to the exact joint distribution, and as a result, the conditional distribution of psi over zeta, and they are not known in practice for us. We can estimate them through different methods that we have in the literature, like the kernel density estimation, random forest, etc. that we have. And the question that arises here is that, can we really trust in the estimates that we get for the conditional probabilities and distributions here? This question was more or less answered with a newer paradigm called distributional robust conditional stochastic optimization, or DRCSO. In this setting, the thing is that we are again minimizing the expected value of this H function conditional or on zeta, but we are minimizing over the worst case distribution that we have in the D set. D set is an admissible set of distribution or ambiguity set that we can choose for our study. Based on what I introduced, we have the CSO and the DRCSO in the literature for the cases that we want to take into account the site information that we have in hand. And on the other side, we need a method to somehow estimate the conditional probabilities. These methods mainly can come from the machine learning community. We have different methods like Nadeau-Watson, kernel density estimation, Dirichlet process mixture models, and so on and so forth. But the thing is that in the literature recently, people focus on these two settings, and then they choose to use CSO or DRCSO, and they use these methods in combination with different predictive models coming from ML community. We see a rise in this type of studies in the literature, but the question is that how we really can compare the different methods and say that one of these methods is really superior compared to the other one in an application. This question was recently answered by Bertimus and Callis. In their recent paper, they are proposing a new performance measure called coefficient of prescriptiveness. In this setting, we are saying that given a data-driven policy X and a distribution F, we can define a coefficient of prescriptiveness like this. We have 1 minus a ratio. What do we have in this ratio? In the denominator of this ratio, we have the expected value of the cost function coming from our data-driven policy minus the expected value of the cost coming from the full information setting or hindsight setting, where your X has really access to psi and it doesn't need any zeta. In the denominator, we have the expected value of H coming from X hat minus the full information one. This X hat is the minimization of the expected value of H of X and psi. And here we can call it the sample average approximation solution, which is well known in the community, where actually F hat is coming from the in-sample empirical distribution, and it is putting the equal weights on the observed data that you have in the data set. If you want to have a closer look at this and what it is actually, how we can interpret that, we can see here that actually in the denominator of this coefficient, we are somehow measuring the distance of the expected value of our cost function coming from the data-driven policy that we claim that we have achieved compared to the one that is coming from the full information. In the denominator, we are measuring the similar distance, but this time this distance is coming from the expected value of the cost of the SAE solution and the full information. So somehow we are comparing our data-driven policy in two different directions. One of them is comparing against the full information setting, and the other one we are comparing our distance to the full information with the distance of the SAA solution can give you compared to the full information setting. So what are actually the values that we can get for this coefficient of prescriptiveness and what they mean? Indeed, when the value of this coefficient is converging to 1, it means that the denominator of this coefficient on the right-hand side is getting close to 0. It means that the distance between the expected value of our data-driven policy is getting as close as possible to the expected value of the cost that we get from the full information setting. This is actually so ideal because it means that your data-driven policy is so good that it is getting back the decision that if you had full information you could have. On the other side, when the coefficient of prescriptiveness is converges to 0, it means that we have for this ratio on the right-hand side we are getting close to 1. It means that the numerator and denominator are equal, saying that the distance that you can make compared to the full information is the same distance that the SAA solution can have compared to the hindsight decision. On the other side, we can say that in this setting, your data-driven policy is not capable of using any side information to give you a better decision compared to the sample average approximation solution, which is blind against the side information, and it is just using the historical information of the side. This coefficient of prescriptiveness has been getting popular during the recent years, and different papers have started using it to somehow compare their proposed methods against other benchmarks. And when they get a better ratio, they are claiming that their methods are better compared to the competitors. But the question that our research was founded on was, if we are really interested to have a higher coefficient of prescriptiveness on the out-of-sample dataset at the end, why shouldn't we try to optimize the same metric instead of the traditional metric that we have? Having said this, I would like to jump to the model that we introduced in this work. We are introducing the distributionally robust prescriptiveness competitive ratio, or DRPCR method. That here we are replacing the empirical risk minimization objective with the coefficient of prescriptiveness. We are maximizing the worst case of this ratio. We are maximizing over X. We have the inf over F, which is in an ambiguity set, and then we have this objective. We can show that under weak conditions, the optimal value of DRPCR is necessarily within the interval of 0 and 1 in the in-sample distribution. But one may ask why we are directly looking into the distributionally robust version of this problem and not the stochastic programming version of that. The answer is here. The moment that we remove the inf over F or the worst case, it means that we have a fixed distribution for F. As a result, the denominator of this coefficient and also the full information part at the denominator will be constant values. So we are maximizing 1 minus expected value of this function, which will be the minimizing the expected value of h of x and psi, which is actually reducing to the CSO problem that we introduced earlier. Here is an epigraph formulation of the RPCR model that I introduced earlier. We are maximizing gamma, and it is subject to minimization of a Q function, which is less equal than 0, and we know that we show that the gamma is between 0 and 1. what is the Q function here? The Q function is the worst case of the expected value that we have here. What do we have inside the expected value? We have the cost function that we have from our actually the data-driven policy minus a linear combination of the cost that we get from the x hat SAE solution and the x prime, which is the hindsight solution. What is the idea to solve this problem? We show that this is a convex increasing function of gamma. As a result, one idea to solve this is using the bisection method. Actually, we can bisect over gamma and solve the left-hand side of 1b, this constraint, and then evaluate to see if it is capable of satisfying this constraint. And we can, based on this bisection method, we can find the maximum value for gamma, which is the optimal value. Then the difficulty will remain on solving the left-hand side of this constraint. For answering this question, we need first to choose an ambiguity set to see how the problem will look like. In our work, we concentrate on the nested CVAR ambiguity set, saying that if there is a discrete distribution of F bar with zeta gamma and psi gamma, where gamma is the index of the distinct scenarios that we have, then we can define the nested CVAR ambiguity set like this. For zeta, which is the observed side information in our problem, we assume no ambiguity. We are assuming that it is the same that we have in the data set. But for the conditional probabilities of psi over zeta, we are imposing the famous constraint that we have for the CVAR ambiguity set. It is less equal than 1 over 1 minus alpha multiplied by the probability that you are, for example, you are getting from your training set as your reference. So it means that we assume no ambiguity in the marginal distribution of the observed random variable zeta, and we are assuming ambiguity just for the conditional probabilities of psi over zeta. Based on this assumption, we can show that under a nested CVAR ambiguity set, the problem that we had for minimizing the Q function, this can be written as a summation of the probabilities that we have for zeta. We assume there is no ambiguity, and we have this phi function for each scenario. And then for each scenario, we can solve a linear program like this, which is the LP representation of the CVAR ambiguity set that we know. And indeed, we can show that this problem of minimization Q can be reduced to a linear program where calligraphic X, the feasible set, is polyhedral, and H function is linear programming representable for all the scenarios that we have. Having said this, let me move to some numerical experiments that we had in this work. I would like to go back to the shortest path problem that I introduced at the beginning. Let's say that you have an origin, you have a destination, you want to find the best route, as I said before, and we want to use the side information that we have in this problem. This is the mathematical formulation of the problem that all of you know it better than me. We have the minimization of the expected value of the travel time that we have. We have a directed graph where we have some nodes and arcs. Psi ij denotes the travel time of a directed path from node I to node j. Xij is 1 if we decide to go from node I to node j, and it's 0 otherwise. And f hat is actually denoting the conditional distribution that we get, and we estimate based on the training data set that we have. We use the same graph structure that Callis and Mao use in their problem, and then we focus on our DRPCR problem, and we want to compare it to some benchmarks. What are the benchmarks that I have? The first one is actually the CSO problem that introduced at the beginning. The other one is the DRCSO that I introduced earlier. But the new one is this perhaps distributionally robust conditional regret minimization. where in the objective function we have the travel time coming from our data-driven policy minus the travel time coming from the full information setting. So we want to compare ourselves against these three methods. Here is the graph that I would like to show you and then discuss more on this slide with you. On the y-axis, I have the out-of-sample coefficient of prescriptiveness, and on the x-axis, I have 6 columns, each representing a specific value of shift. And then I'm showing the statistics of the 4 different methods based on 50 samples. The first column on the left-hand side is referring to the setting that we are generating a training, validation, and out-of-sample data set in the same way. And then we are using the different methods to solve the problem and test them on the out-of-sample setting. As you see, more or less, all of the methods are showing similar behavior on that. Then we were interested in the setting that, let's say, for the travel time on the shortest path problem, we have something in the training data set, but we can think of a situation that we have a distribution shift. Let's say you train your data for a specific days during a month, and then an event is happening in the city. So you are actually observing a new a shifted value for the mean of your travel times on different routes in the city. So as a result, we keep this previous setting for the training set, but for the out-of-sample setting, we are assuming that we observe a shift in the average travel time on the arcs. Here we are imposing up to 20% distribution shift. And as you see here, the PCR is starting to show some increase in terms of the coefficient of prescriptiveness. And as you see, as we are increasing the magnitude of this distribution shift, the DR-PCR starts to show a more and more obvious difference with the other methods. And at the same time, focusing on any of these methods, you will see that as we have more distribution shift, the performance of each method is decreasing because we are exposed to more uncertainty in our problem. The interesting thing is that, for example, let's have a look at the 60% shift. You'll see that the other 3 methods, they are showing more or less a negative coefficient of prescriptiveness, but still the RPCR is capable of providing a positive out-of-sample coefficient of prescriptiveness. But what can be a possible reason behind this? For that question, we can focus on this slide, on this graph. This is the same graph, just on the y-axis. This time, I'm showing the average distance to the sample average approximation solution. We are showing the L1 norm distance of our data-driven policy compared to the SAA solution. As you see, for the CSO, DR-CSO, DR-CRO, they are not, you are increasing the magnitude of your distribution shift, the methods are not capable of adjusting themselves to the distribution shift. But for DR-PCR, as we are increasing this shift, as you see that the average distance of our data-driven policy is getting more closer to the SAA solution that we have. This means that since we are using the SAA solution as a benchmark, the DR-PCR is capable of using a different type of regularization in it, and then it can adapt itself to the SAA solution and getting close in the situation that it needs to be. Having said that, I would like to conclude my talk at this point with 2 takeaway messages. First, we show that under the nested CVAR ambiguity set, optimization of the coefficient of prescriptiveness in this DRO context leads to a special case of solving a set of linear programs. And when roughly speaking, the mean of the unobserved random variable is exposed to a distribution shift. The out-of-sample coefficient of prescriptiveness achieved by DR-PCR policies are higher than those obtained by the alternative methods. So I come to the end of my talk. The online version of our paper is online. You can find it on a link on Eric's website as well. And I would be happy to get any comments or suggestions or questions that you might have. Thank you.